Okay, so yeah, let's get going. So again, there's a quiz, so do the quiz. Um, and homework 1 is due. And I'll post, and homework 2 will be due in 2 weeks. I'll do it tonight. I'm just trying to run some final checks on it. Yeah, and so today we're just going to finish up. So the plan is we're going to finish approximation methods today. And, you know, all the approximations we're looking at are approximations to just diagonalizing the Hamiltonian. And we're going to move on to time-dependent Hamiltonians, which we looked at a little bit when we did the Rabi oscillations. But there we solved things exactly. So what we'll be doing is trying to approximate solutions to the time-dependent Schrodinger equation. So that's the idea. And that'll lead us to a discussion of path integrals and propagators and things like that. So that's the plan. And so I wanted to finish up with the degenerate perturbation theory. And the last place we left off is we just rewrote the eigenvalue problem in a different way, right? We rewrote it by using projection operators. And we had written down this kind of form here. So yeah, this is a projection operator. The nth eigenvalue is, you know, degenerate, and the projection operator here projects you into that degenerate subspace. And this is all acting on the perturbation times psi. I guess I was using phi's. The states that are in the, it's the eigenstate that's perpendicular. It's the components of the eigenstate that are perpendicular to degenerate subspace. And this was all equal to En minus, that's the full eigenvalue, H naught minus lambda. And then it's the projected part of the perturbation that's in the parallel subspace. And that's all acting on psi in parallel. So yeah, and then we had lambda, sort of the opposite equation where we project onto the perpendicular portion. And otherwise it's sort of similar looking, except now you're projecting onto the perpendicular part here. So that was what we got. It's just rearranging the eigenvalue equation and projecting it onto the parallel and perpendicular subspaces related to the degenerate eigenvalue. So just to remind you what the projection operator is, the Pn parallel, it's just you take a sum over all the degenerate eigenvectors of the degenerate unperturbed state. So these are the degenerate unperturbed states. So that's what we had, and of course the perpendicular one is just the identity minus the parallel one. And all we're doing here is we're just expanding our eigenstate in terms of a parallel and a perpendicular component. And we're just expanding the eigenvalue equation, right? The A, En, phi n. This is H naught plus the W phi n. So that's where those two equations come from, but they're handy because if you're away from the degenerate subspace, then this operator here is invertible. An operator is invertible as long as when it acts on a vector, it doesn't give you a zero ever. So this operator is invertible. Why? Because it's acting on a state that's away from the degenerate subspace. So this thing will not blow up. So we'll only really worry about if it blows up if we set lambda equal to 0, say, then these would just be the unperturbed eigenvalue minus the unperturbed Hamiltonian. And the only time something bad can happen is if you're in the space where there's a degeneracy. So if we break up the problem into this parallel subspace and the perpendicular one, then we can just work with the perpendicular one and invert the operator and then see what happens in the parallel space. So that's the idea. So what do? We just invert this operator to solve for phi of n perp. Take this equation. We solve it, and what do we get? Well, we would get lambda pn perp here. Then we can put in the operator. So this pn perp, of course, commutes with this operator because it commutes. Yeah, so it commutes with this portion. So anyway, we can, and the Pn, remember, so well, I'll show you. I'll just write out the answer here. So this is the inverted operator here. Right, and then no, so we can put in, since everything's already in the perpendicular subspace, we can put in another factor of Pn perp here on the left-hand side. It doesn't hurt anything. So that's what we can do. And then the rest of it is just this operator Pn perp, the W phi n parallel. So you always want to sandwich your operators between the projection operators, kind of like we did here with these W's, because that's the transformation rule for operators. If we want the operator that's in the projected space, then we would multiply by the projection operator on both sides. So then it makes sense if we look at like matrix elements and we sandwich that operator between bras and kets, we want the two projection operators to project both the bra and the ket, right? So it's sort of, so it's nice to kind of keep things symmetric that way. So what we did here is you took the second equation, we inverted it, and then we just stuck this projection operator out here, so that what is this thing? This is, well, clearly this is going to be this big operator here right? This is the inverse of this guy, and it's in the perpendicular subspace. It's acting on states that live in the perpendicular subspace. So yeah, and now what you can do is you can take this and you can substitute this relatively long equation back into the first equation. So you can now take this solution and plug it back into here, into the first equation. And the first equation is just fine. It's just we can't invert that operator, the equivalent operator here, because it's in that parallel subspace where you can get things blowing up in the denominator. As I showed you in regular perturbation theory, if your unperturbed eigenstates are degenerate, then you get blowups in your denominators when you're doing like second order perturbation theory and so on. But so that's, in terms of these operators, that's the same as saying, that this energy difference operator is not invertible. So that's the same kind of statement. So you can plug that back in and you get this kind of, well, not so pleasant equation, I guess, but it's okay. We get that. So I'm going to now write this left-hand side. This left-hand side is En minus H naught minus lambda Pn parallel, W Pn parallel, Phi n parallel, okay. And then this right-hand side becomes a little bit more complicated because we're sticking in for phi perp there, our new solution. And now there's going to be two factors of lambda. So there's actually a lambda squared term here. Then we have P and parallel, W, right? That's the first part. And then we have P and perp, and we have this inverse operator, En minus H naught minus lambda perp, Pn perp. The inverse, Pn perp, W phi n parallel. Okay, and this might not look any better, but it is better because look, we just have something that lives in the parallel subspace on both sides and nothing else. Everything else is just operators. We know what these operators are. They're these guys. And similarly, Pn perp is the identity minus Pn parallel. So we can use completeness and stuff like that to write these things out as sums over projection operators. So it's all kind of sensible, even though the equation looks kind of ugly. But it's not so bad because we also have in here these lambdas. So remember, we're doing perturbation theory. So as usual, we would want to go order by order in lambda and see what we get, right? So what we've done here is we've taken the eigenvalue equation, we've decomposed it into a piece that's in the degenerate subspace and a piece that's not in the non-degenerate subspace. The non-degenerate subspace is okay. We can invert the eigenvalue equation. We know that there won't be any nasty blowups because we're away from any degeneracies. Then we use that solution to plug back into the degenerate subspace piece so we can figure out what happens there without doing any operator inversions that might give us denominators that blow up. So that's the idea. And so far we made it to here. But now we're just looking at what happens to states in that degenerate subspace. So any questions about that? Okay, so then let's get to the stuff. So let's look at leading order in lambda. So that's lambda set to 0. So if we drop all those, those guys, right, what do we get? Remember, this is regular perturbation theory, so we'll also have to expand these guys. These are the eigenvalues and the eigenstates in terms of lambda. So not only are there lambdas just hanging out here, you also have the lambdas that are in the expansion of the eigenstate. All right, so this thing is En, the unperturbed one, plus lambda En1 plus ... And these guys are also, there's going to be the unperturbed one eigenstate plus lambda phi parallel, the first correction, right? And so on. The parallel, again, just means that you can take your state and apply the projection operator, the p parallel projection operator to it, and you'll get the components that are in that parallel subspace. Anyway, so to leading order, you would just send lambda to 0 everywhere. So then this becomes, let's see. This becomes En0 minus H0. This goes away, and this is phi n parallel 0 is equal to 0, right? That's sort of sensible, right? Because that's just the unperturbed equation, right? That's just, if you don't have a perturbation, then you just get the original eigenvalue equation. So that's kind of a silly case. It gets a little bit more non-trivial once you get to first order in lambda. And then you start thinking about what's first order in lambda. Well, you certainly have this lambda En1 piece. So we'll do that. Lambda En1. If this piece has a lambda En1, then we can only really take the 0th order portion of the state. So that's phi parallel 0, right? Because we're just looking at all the terms that are linear in lambda here. Over here, this term already has a lambda in it as well, so there's going to be a minus lambda Pn parallel, W Pn parallel, again acting on the unperturbed bit. And this term over here, there's a lambda squared out front. So this whole thing is 0. So to this, so what do we get here? Here we just get that the first order correction to the energy, that just satisfies the eigenvalue equation for the W operator, right? That's what we had before. I argued initially when we started degenerate perturbation theory that the first thing you want to do is diagonalize W in your degenerate subspace. And that's indeed what this equation is telling us, is that to leading order, what you want to do is solve this eigenvalue equation. This is the matrix, which is W in that degenerate subspace. And this is the eigenvalue, the correction. So the correction is the eigenvalues of W in that degenerate subspace. So that's exactly what we would expect, right? So yeah. Any questions about that? This first order term. You seeing what I'm doing? I'm just going order by order in lambda and looking at the equation that you get at that order in lambda. That's a usual thing to do. No, we good? So we've proven now using this projection operator method that what you want to do to leading or to sort of first non-trivial order in lambda is that you want to diagonalize W in the parallel subspace. And now we can also look at the state corrections, actually. We can look at them because we actually have an expression here for the state up here. And we can look at it order by order in is there really no questions about this part? And it's a sort of a little bit of a tricky calculation. Okay. Let's see if you might have wondered, this is maybe something that I'm wondering, what happened to the first order terms that come from this this second order guy multiplying just the, this first order guy multiplying the 0th order stuff over here. Well, that part is just 0 because En 0 - H naught acting on lambda phi n parallel 1. That should just give you 0. Because it's in that parallel subspace, right? So that's the funny thing, right? If it's in the parallel subspace, that means this entire vector is written as some linear combinations of your degenerate unperturbed states, these guys. See, because the projection operator just extracts all these guys. So it's in that degenerate subspace. So whenever it acts, whenever this guy, whatever linear combination it is, no matter what the correction is, whenever it hits the H naught, it'll just give us En 0 again, because it's in that degenerate subspace by definition. See, it's the parallel guy. So it's En 0 - En 0. So that's just 0. In case you were wondering. I was wondering for a bit, but So it's true that the only terms that survive this are just these guys, which tell you again that what you want to do is diagonalize W in the parallel subspace. Okay, so I guess I waited long enough, so no more chances for questions. We have to move on to the state correction. So the state correction is comes from just this expression. We can look at this too, order by order in lambda, and see what happens. So to leading order, you have lambda phi perp n, and we're going to include the label for the, and it's the leading order, so it's the first state correction. So that's equal to lambda. And now if we look back at what the phi perp was equal to, right? So there's already a lambda out here. So we don't need any more lambdas. We're done with the lambdas. We get a lambda here from expanding this guy. That's this first order correction. And then the rest of this lambda just goes away because we already have a lambda. So we're already to, you know, first order in lambda. So you get this guy, and we don't need to expand the en either. So it's just the zero, it's just the unperturbed eigenvalue, because we already have the lambda, minus h naught. And there's no lambda from the w part, so this just becomes inverse. And then pn perp w. And this guy should be phi parallel the zeroth order, the zeroth, the unperturbed piece, like that. So that's what it is. And it might, and again, what you want to do is just expand these things in terms of your completeness relation. So what this guy is, and again, the lambdas cancel on both sides. This guy is, it's a, you can put in completeness relation, you can put in sum over states for the perpendicular subspace. What are those sums? It's just all the m's that are not equal to n, right? It's the perpendicular space. So it's the it's this operator in that perpendicular space. So it's over all the states that are not, all of the unperturbed eigenvectors that are not equal to n, right? It's away from the degenerate subspace. So it's for all m not equal to n. And what's this operator? Well, if we use the unperturbed vectors as your basis for your states, well, then h naught is just diagonal in that basis. And so it's just the difference in energies there. And then the unperturbed portion, the parallel state, well, this guy is just n comma s, right? So then the matrix element that we want is just w acting on this guy, and it's n comma s. And again, we need the ket here, because it comes from, you know, this operator here is just this guy right here. This is equal to sum over m not equal to n of the projections onto those m eigenvectors, en0 minus em0. See, it's just it's just that operator in the. Sorry, I should have grabbed this other projection operator here. It's this guy. This is just the inverted operator in the perpendicular subspace. So it's a sum of projectors over the non-degenerate portion of the space, and the operator is diagonal in that basis. So it's just, you know, 1 over the difference in those eigenvalues. And this never blows up, right? Because m's never equal to n, and we're saying that the m's are all, you know, non-degenerate. So nothing bad happens there. And this is fine. So we have this, and this is what you would expect for the first order correction. in non-degenerate perturbation theory, right? This looks exactly like what we had before when we didn't worry about degeneracy. But notice that's only true. That's only true in the case where we're in the perpendicular subspace. In the perpendicular subspace, that portion of the correction to the state, it's the same as regular perturbation theory, non-degenerate perturbation theory. So now we have to go back and examine what happens to the parallel situation. We have to go back to this equation and look what happens to the state here. And this is where it gets a little bit more complicated. The equation's a little bit more complicated. So what we want to do is rearrange this equation and put everything over to one side. That'll be convenient because then we'll be able to see what's going on. So we take this equation and we just pull everything to the other side. So again, this is for the perpendicular portion of the state correction. We get just like regular perturbation theory. And here we're going to do it for the parallel portion. So if we rearrange this equation, what does it look like? Again, it's not a very pleasant equation, but it has within it all the information we need to do perturbation theory. So we rearrange it. We have this stuff. We're just going to subtract that lambda squared long term out here and put it on the other side. Oh, this is acting on phi parallel. That's equal to 0. So I've just pulled that complicated term over to the other side, and I've also dropped this portion. Why did I drop it? Because if we look at it here, this is a lambda squared times lambda term. So, well, this is inverse, of course, but if we start Taylor expanding this inverse operator, this term will only contribute to order lambda cubed, right? So to order lambda squared, this equation, if I rewrite it, only this part will matter. We don't want to put any lambdas in here because that's just going to give us a lambda cubed term. So I can put up to order lambda squared. That's what our equation looks like. So now we kind of have to stare at this equation and sort of see what is going on. And what's going on is that if you stare at this, this looks just like a perturbation problem, right? It's not very obvious to see, but it kind of looks like it. Remember, the original eigenvalue perturbation problem would just be like this. Right, this is the original perturbation problem. This is an OG perturbation problem. But you see, this equation looks just like that. This is the eigenvalue we want. Now, instead of H naught, what we recognize is we can define a new H naught because we know everything about this guy. What is this operator? This is H naught and the perturbation in the parallel subspace, right? But we know that we're going to diagonalize this piece anyway. So this guy here is going to be already diagonalized. Remember what I told you, if you have a degenerate space, then you want to diagonalize the perturbation in that space. So you already know what the eigenvalues of those things are in that parallel subspace. So that this is already diagonalized, so we can interpret this whole thing as a new unperturbed Hamiltonian. So this is our new unperturbed Hamiltonian. Because this part is already diagonalized. We already saw that we want to diagonalize that piece to get the first order corrections to the energy. So once you found these first order corrections to the energy, right, those are the eigenvalues of this thing. When we're calculating the state correction, we already have those eigenvalues and eigenvectors at our disposal. So this part's already diagonalized. Again, these states NS, they diagonalize, of course, both H naught and PN parallel W, PN parallel. Both of them, right? That's how they were defined after all. And so then the rest of it is a new perturbation. This is our new perturbation. Okay, so this looks just like another version of their perturbation problem. And we're going to use that to our advantage, right? So let's call this new perturbation lambda W bar. And what is this W bar? Well, it's just, you know, the rest of that stuff. It's got a lambda out front, and it's got a PN parallel, W, PN perp, EN. And again, these are going to be the unperturbed ones, of course, because we don't want to have more powers of and you see everything is working out so nicely. This guy is going to be in the perpendicular subspace. So that means that inverse operator is perfectly well defined, because we'll never, you know, hit degenerate eigenvalues of H naught. So that's the new perturbation. And so what we can do is we can just calculate the state correction for that perturbation using the same kind of, this kind of formula right here, right? Because everything is fine now. This is like a redone perturbation problem, and we can just write down what the state correction is for this new problem. And this new state correction is phi. And again, remember what we're calculating. We're calculating the first correction in the parallel subspace to these phi n states. That's what, you know, it's these guys. And so that correction is, what do we get? We again get an operator here that's in the perpendicular subspace. But here, what are our unperturbed Hamiltonian? These are the relevant eigenstates of the unperturbed Hamiltonian, and they have our new, so they call it H naught bar, right? Which is H naught plus lambda PN parallel W PN parallel. Let's say it's got eigenvalues. What are the eigenvalues? The eigenvalues are just going to be En 0 plus whatever those eigenvalues of W are. So they're going to be some lambda times some little W and S, right? They might depend on S, right? Because when we diagonalize the W, it'll have different eigenvalues depending on the value of S, right? So those are the eigenvalues. So when we do the state correction, what is it? It's, well, we're going to get a sum over S prime not equal to S. Remember, we're in that parallel subspace, so we only really care about these states. We get a difference in the eigenvalues between S prime and S. The En not just cancel. So down here we get lambda W n S minus lambda W n S prime. Right, that's just by analogy to, this is just the first order correction for perturbation theory. It's just this newly reinterpreted perturbation theory. And then we have this relatively, not so pleasant perturbation, this W bar, right? So let's just write it out. Lambda Pn parallel, W Pn perp. Then we have these differences in so we just substitute in for omega bar. Okay, so now some nice things happen. First of all, the lambdas here cancel. Second of all, we know that this portion here, I already told you what this operator is. I have it up here, right? This is the same operator. It's just this guy. So we can substitute in. Let me just draw a little arrow, I guess. This is, we already, so this is just going to come in here, go to there, right? So we're going to substitute that part in. And what do we get? We get that this is equal to sum over S prime not equal to S of 1 over S minus B and S prime. Then we have our sum over M not equal to N. And again, we have NS prime. Then we have what? Well, we'll have these W's. And we'll have our completeness in the M's. And these are just, again, W and S. And it's all divided by the differences in the eigenvalues of the unperturbed Hamiltonian. Just plugging this in. You might wonder where this Pn parallel went. Well, nowhere. Pn parallel can just act on this guy, this vector here, the NS. See, it's already in that parallel subspace, so this doesn't do anything. So that's the answer. And oh, and I'm missing, of course, I'm missing, well, what am I missing? What's wrong with this equation right here?
You're missing a vector on one side.
I'm missing a what?
You're missing a ket.
Yeah, I'm missing a ket, exactly. So I'm missing a ket from this guy, which was part of a projection, right? We're summing over all the S primes not equal to S, and this was a projection onto that space. So there's an extra N S prime ket, which just comes from breaking up this guy. Yeah, that's right. So I just forgot to put that in there. So all of this is this is just a number, right? It's all this is multiplying ns prime the ket. That's right. So yeah, so again, how do we do this? We took the equation for the parallel portion of our eigenvector, and we reinterpreted it as a new perturbation theory, where our new unperturbed Hamiltonian includes the original perturbation in it, but just the part that's in that degenerate subspace. And why? Because we know that the first thing to do when we studied the corrections to the energies is that we know we're going to diagonalize that part anyway. So we can just group it together with our original unperturbed Hamiltonian, and we already know what the eigenvalues and eigenvectors are. The eigenvectors are just those, whatever diagonalizes W, and the eigenvalues are just the unperturbed energies plus lambda times the eigenvalues of W. And then all the rest of this stuff is going to be our new perturbation. And once we have that set up, we can just write down the first order correction to the state, because we have fixed all the issues with degeneracies now, provided that, of course, these eigenvalues are not degenerate. That could be an issue. But provided that these guys are not degenerate, then this unperturbed Hamiltonian doesn't have any degeneracies in it, right? So we can just use regular perturbation theory. And what do we do in regular perturbation theory? We do this. This is our state correction, where we sum over all the m's not equal to n for that particular. So I should put an s here too. And so what do we do here? So we just sum over all the s primes not equal to s. And we have this ns prime projection over the difference in eigenvalues. And of course, this part of the eigenvalue drops out. You just have a difference between these w's. And then the rest of it here is the matrix elements of the new perturbation. And these matrix elements of the new perturbation, we can just rewrite them like this by plugging in what this operator is, which I already sort of calculated up here. What it is. So that's what's going on. And it's kind of neat because this is like a W squared term, right? There's two W's in there. So it's really kind of weird when you have degenerate perturbation theory. The correction to the state in that degenerate subspace actually has an extra term in it that you wouldn't normally expect. So let's write down the whole thing, right? So this is the portion in that parallel space. And this is the portion in the perpendicular space. So we just have to add them together to get the full first order correction to the state. Again, it's the portion that's parallel plus the portion that's perpendicular. And okay, so I guess I'll just start with the perpendicular portion. This is easier to write down. It's just this guy. So we have a sum over m not equal to n of these m, w, n, comma, s, these guys, divided by en0 minus en0. And now we're going to rewrite we can exchange these summations. See, nothing about these w's here depends on m, so we can exchange the m and s summations. And what we're left with is this m, which this part comes from that perpendicular subspace. But we get this extra term, which again, we didn't have before when we did this kind of naively. It's the portion of the correction that's in that degenerate subspace. It does exist. And the funny thing is that it's got another factor of W in it. And that's this guy. So there it is. That's the first order correction. So yeah, so let me summarize then the degenerate perturbation theory. This is as far as we're going to get with it. Our corrected states are going to be the NS's, which again, remember they diagonalize. Maybe it's better to put H naught plus P and parallel W P and parallel. It's a nice way of thinking about it, right? Because we're going to diagonalize the W in that degenerate subspace right away, or kind of a better way to think about it is that we have a new unperturbed Hamiltonian, which is H naught plus the diagonalized W, because we can just lump them together because the entire matrix will be diagonal in this basis. And then we'll have lambda, phi, and S1, and that's just this guy up here. What I wrote down there. And what about the energies? The energies are, of course, the unperturbed guys plus lambda, the matrix element, the eigenvalues of W there. These are going to be eigenvalues of, well, this includes all the, I shouldn't really write that. This includes all the matrix elements if we're in the non-degenerate part also. So this includes like any M's that are not equal to, I won't write eigenvalues. Anyway, so that's, yeah, so these are just the matrix elements of W, and again, you diagonalize W in that degenerate subspace. So, but in the non-degenerate subspace, you just take the matrix element, diagonal matrix element, as you would for regular perturbation theory. And then there's the lambda squared correction, which is just same as before. It's these matrix elements squared divided by En0 minus Em0. And that's it. That's really the whole picture of degenerate perturbation theory as far as we're going to go. And again, usually in undergrad, you would have probably learned about diagonalizing W, but you probably have not seen this thing that is the portion of the state correction that's actually within that parallel subspace. It's actually of order W squared, which is really weird, even though this correction comes in at order lambda. Really kind of trippy if you think about it. You have a W squared correction that comes in at order lambda. Why? It's because if you have a degenerate subspace, then it's this denominator. Then the difference in those energy levels when they split due to perturbation, the splitting, right, is going to be of order lambda. And we divide by the energy splitting. So there's going to be a cancellation of one factor of lambda. And that's why it comes in at order W squared, right? Because the energies are very closely spaced together when they're degenerate originally, right? If you, so yeah, so that's the idea. It's these little W's that had lambdas attached to them. The difference in energy levels, is of order lambda. So you need a W squared to kind of cancel one of those factors of lambda. And overall, that term W squared over a small splitting is going to be of order lambda. So it's going to come in at first order in the perturbation theory. Okay, any questions about perturbation theory? It's a little bit tedious, but conceptually it should be pretty straightforward in the sense that what are we doing here? Again, it's just taking the eigenvalue equation and just keep kind of hammering away at it. And if you're ever, and the idea of degenerate perturbation theory is just that you can't invert these operators sometimes. So what you do then is you just break up your states into a piece that you can invert, the perpendicular piece, and then you just leave the parallel piece alone and you plug in for the perpendicular piece, and eventually you should get into this form. This equation is actually quite powerful. If you just, this is the whole thing, this thing in blue. This is that equation in that parallel subspace. You can just keep going with this. If you ever wonder, like, what's the second order state correction in degenerate perturbation theory? Well, you would have to go to the next order in lambda, right? You have to look at the lambda squared terms. And it gets a lot more tedious, but conceptually not any more difficult. It's just, yeah, I don't know, it's just the way it is. It just gets a little bit nastier because yeah, I mean, you'll have to start thinking about this this term right here. This will start contributing. So yeah, so you have this equation, and if you want to know what happens to the perpendicular portion, the other important equation is, of course, this one. This gives you order by order in lambda what the perpendicular portion of the state is. And again, you can expand this in lambda and get the higher order corrections. But to be honest, for most practical purposes, people basically never go beyond these equations. So that's why in undergrad classes, you often just kind of memorize these. And even this part is sort of, well, it's important, but you know, I don't know. It's often overlooked, maybe. Yeah, so for practical purposes, if you have degenerate perturbation theory, you have some degeneracy in your unperturbed Hamiltonian, what you just do is just diagonalize W. And then since the energy corrections then don't change at all, this looks exactly like non-degenerate perturbation theory. The only place where you run into some issue is with this funny state correction, but people usually don't worry about the state correction too much. So it's usually what you just have to remember. If you have a degeneracy, say, oh, well, I have to diagonalize W, so let's do that. And then I can just apply, you know, the usual things I remember from regular perturbation theory, just the first two corrections, the energy, and, you know, the state correction, well, I don't know. Yeah, I don't know. I don't know how important this term is. I don't actually use perturbation theory day to day, but yeah. Any questions about that? Okay. I'll clear this then. So the last kind of approximation we're going to look at is the WKB approximation. Is Wenzel, Kramers, and Bruin, I guess. Sometimes they add a J for Jeffries, but also it's called the semi-classical approximation. And the basic idea is that we have a slowly varying potential, and we're going to focus on one dimension. Although you remember how you can go to spherical coordinates and turn a 3D thing into a 1D thing. So you can do WKB that way too. You can also just develop it in 3D in general, but we're going to just do 1D The generalization is not particularly interesting. And the other idea is that we're somehow at a large momentum. And remember what that means. Large momentum means, and of course that's h bar k. Remember, large momentum, it means very wiggly wave function. Because if we have a free particle, you know, the wave function is plane wave, and you know the wiggliness gets larger with larger k. So what's the idea is you have a potential, and of course you can use this to study all kinds of things. You can study transmission, you can study scattering, you can study bound states, but it's the usual thing where we have a potential V and we have some fixed energy. And the idea is that we're going to try to approximate the quantum problem using the classical limit. And in the classical limit, of course, if you have a situation like this, you have a particle living in this potential, it'll just rattle around, right, inside this region. And whenever the total energy hits the potential here, that's where you're done, right? The particle just turns around there because you can't have negative kinetic energy. So again, so this is a sort of, in here, it's the classically allowed region. And here it's forbidden, classically. And otherwise, the wave function in here, if it's a particle that's large momentum, it's going to be a very wiggly wave function. All right. And that's kind of the basis of WKB, is trying to take advantage of that picture where we know classically the particle is not allowed inside these regions. And in here, it's just going to be rattling around. And these points here are called turning points. They're where a classical particle would turn around. That's why it's called that. So that's kind of the idea, but let's actually do it. You know, it's as usual, again, this is another approximation for solving the Schrodinger equation. So let's again write it down as we do. And let's put the eigenvalue on one end here. Okay, so what we do is, the idea is, since it's the classical limit, we also want to send h bar to 0. So we're gonna somehow the h bar is gonna be small here. So roughly the idea is if h bar is small, right, then to compensate all this stuff that doesn't change the potential, this derivative will have to be big, and the derivative is something like the momentum, right? So if h bar is small, then the variation of psi, the wave function, it has to be larger, so it has to be more wiggly. So as you send h bar to 0, you're in the regime where psi is very wiggly, so that the two effects kind of cancel. This is very rough intuition for what happens, and that's kind of the approximation. But before we do all that, as usual, when we're actually solving a practical problem, it's nice to non-dimensionalize. We're going to try to hammer away at the Schrodinger equation, get it in a form where there are no more weird constants left and there's just dimensionless parameters. So we define a z, and you can non-dimensionalize in a kind of abstract way. We can say z is a non-dimensional length, which is just our x length divided by some L. And then we're going to have some non-dimensional energy, which is our energy divided by some characteristic scale. This might seem like a silly thing to do, but you'll see that it's not. If we do that, you get that this is h bar squared over 2m L squared, two z derivatives. We have V LZ minus epsilon E naught. And we can divide through by, and this of course is going to be psi of z. We can divide through by 1 over E naught, because all this is equal to 0. And what we get is h bar squared. I'm going to multiply through by a minus sign over 2m L squared E naught, two derivatives with respect to z. And then we have plus epsilon minus V LZ over E naught. We got this kind of term. All of this is multiplied by psi of z, and that's equal to 0. And why is this convenient? It's because now everything is non-dimensional, and this thing is a number. This is a number. It doesn't have any units, and this number, which is called delta, actually it's square root of this, so delta squared is h bar squared over 2m L squared E naught. We're going to say that that number is very small compared to 1. Now, I didn't say what the length scales and the energy scale is, but whatever it is, this is the condition. This is the condition that we would want for WKB to work. And so what we can do now is rewrite this equation as follows, right? We can divide through by delta squared, and what the equation is the z squared is equal to minus q squared, which is this function. This function is q squared. This epsilon minus this guy. It's just going to be some function of z. It's q squared, some function of z. Over delta squared psi. And again, where q of z is the square root of epsilon minus VLZ over E naught. So we've hammered away at our Schrodinger equation until it has this form. And now we can start thinking about what happens here. And the idea is, if q of z is slowly varying, if this thing right here is roughly a constant, right, then this equation would just have exponential solutions, right? If this quantity is approximately constant, then of course the solutions to psi are just going to be proportional to E plus or minus I Q Q over delta Z, right? That's sort of, that's what it would be. And in general, Q times Z would just be some other function, would just be plus or minus I, some function, which I'm going to call phi of Z divided by delta. It would be Q times Z in the case where Q is approximately a constant, but this would be the general form of the solution. And this is the key of WKB, is you use this as an ansatz. You do a variable transformation where you say, let's just look for solutions that look like that. They will look like some constant times E to the I, some other function phi of Z divided by delta. Now we haven't done anything. This is exact still. This is just like a variable transformation or whatever. But the intuition is that if Q is really slowly varying, then this is a pretty good ansatz, right? That's a pretty good thing to try to see if we can simplify the equation or make some sense of it. So let's substitute this in. We take this and we substitute it back into here. Right? And we have to use chain rule and stuff. What do we get? Well, we get so we can put the delta squared back on the other side. So we get delta squared dz acting on the first application of the chain rule here. It's I over delta d phi dz e to the I phi over delta. Right, that's the first application of the chain rule, that second derivative. We're going to put the q squared on the other side. So all this is equal to 0. Okay, we can do the chain rule again. This is I delta squared over delta. Now we have two derivatives of phi. And this is e to the I phi over delta. And just like on your homework for this week, you have to make sure when you do the chain rule that you hit both this guy and you hit that guy again. So you'll get another factor of 1 over delta here when you do the derivative hitting that exponential again. And you get two factors of this first derivative. Right? And then plus q squared e to the I phi over delta. That's equal to 0. So what is this? Well, the exponentials all cancel. And over here, you get one factor of delta cancels. Both of these deltas cancel. So you get I delta. You get two derivatives of phi, which I'm going to denote as phi double prime. You get minus phi prime squared plus q squared is equal to 0. Now you might say, well, this is terrible. Why would we ever rewrite our nice equation that was like this, that just had two terms, to one where we now have this first derivative and things look terrible. But it's better because now instead of, see, the delta here is very awkward, right? You can't send delta to 0 here because you don't even know what to do. It means that the second derivative vanishes. But then how do you even interpret that equation and be like psi is equal to 0? Very bad. But here, once we kind of use our intuition for what happens if q is slowly varying, we rewrite our equation. We haven't done anything. This is an exact mapping. We rewritten it in such a way that when we send delta to 0, it's much more sensible, right? If we send delta to 0, I can actually solve this equation. That's fine. It's just phi prime is equal to q. I can integrate that. That's perfectly fine. And so now we can apply perturbation theory, in a sense, to this equation. We can start expanding it order by order in delta. And that's what we'll do next time. And hopefully finish this off. We're going a little bit slowly, I guess, but it's okay. Next time, what we'll do is we'll just say, well, let's do a Taylor series expansion of phi. We'll say phi is phi naught plus an expansion in delta. And we're going to look at this equation order by order in delta. So we're going to do a perturbation theory in delta. And that's what we'll do next time. We'll solve this equation order by order, and we'll see what kind of solutions we get. Just to show you, if there's no delta at all, then phi prime is equal to plus or minus q, and that's very easy. Then phi is just the integral of q, d z. And that makes sense, right? Because if q is a constant, then this will just be q times z, right? The integral of a constant is just the variable, so it would be q times z if this big Q is just a constant. And that makes sense because then we have to, if Q is a constant, then, it has to be Q times Z for what phi is, so that it's just consistent. So next time what we'll do is we'll do it systematically, more rigorously, order by order in delta, and see what happens. All right, any questions about that? And we'll derive a condition by what I mean by slowly varying. But again, so far we haven't done any approximations. This is just hammering away at the Schrodinger equation and rewriting it in this form. Haven't done anything. It's just mathematic manipulation of this guy. But we'll see it's very useful manipulation.